This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. Okay, so what I want to do for the rest of the class, and again, we'll probably get out a little early, but I want to talk about engineering problem solving. So up there you see my super fancy intro to engineering rocket, right? So let's think about this here. Let's draw our super fancy rocket, right? We've got a rocket, it's got some fins on it. Right, I'm not the best artist, but that's fine. Put a little thing on it. Rocket, everybody buy that? It's a rocket, we're good. All right, our job is that we need to get this thing into space. How are we gonna do that? Maybe it doesn't even, maybe we're just out in our backyard and we wanna launch our rocket to 1,000 feet, right? It doesn't even have to get in space, don't worry about that. But how are we gonna do that? Tom, what do you think? How are we going to get our rocket into space? What propulsion we're going to use? Okay, good. So if my rocket weighs m, mass m, how much oomph does it take me to get up? It's physics. What's a force equal to? All right, so that's a good start. All right, so we have force equals ma, and in this case, what is a? Acceleration. Well, but if we're trying to make our rocket go up, what's our a? What do we have to overcome? Gravity. There we go. Gravity, right? So if I want to take, let's imagine this trash can's full and it's super heavy, right? If I want to take this trash can and I want to move it from here to here, what did I just exert on that trash can? Force. Force. What did I do? Did I put work into this trash can? What is work? Physics nerds, what is work? Force times distance. There's my man. All right. Oh, now I just lost my thingy. Did anybody see where I put my... Oh, there we go. All right. So we have force equals mass times gravity. What did you say work was? Force times distance. All right, so our distance is what? Yeah, 1,000 meters in this case, right? And our force is what? Mass times gravity. So if I need to lift my rocket of m to 1,000 feet, how much work do I need to put into that rocket? The formula, right? I don't need an answer, right? But the formula, right? You guys get where I'm going, right? So work, what's required to lift our rocket from the ground to whatever distance we want is, walk me through it. M times what? Times G times what? D. Has anybody seen that formula maybe once or twice or 19,000 times in their life? In their physics class, right? All right, so now we know how much energy, right? Because what is work? Energy, right? Now we know how much energy it's going to take us to get up. So now, how are we going to do it, Tom? You use a certain amount of fuel. You just nailed it. All right. So how are we going to do this? What we're going to do is we're going to figure out how much it takes to lift the rocket, right? So you guys just nailed it. Force times distance, mass times acceleration, which is gravity. How are we going to lift the rocket? We're going to put in fuel. How much fuel do we need, Tom? The amount that we need? Yeah, so if, let's say we're using super awesome jet fuel, right? That's SAJF, right? SAJF company sells us super awesome jet fuel. If I burn 1 kilogram of super awesome jet fuel, how much energy do I get out of that? I don't know. How much ever energy it is, right? But fundamentally, you guys understand that the chemical side of this now, right? So this was what? What was this? Use a different color. What class was this from? Oh, that's weak. Physics, that's weaker. We might have to use a purple one. All right, whatever, you guys get it. Physics, exclamation, all right? So that's physics, and we're using what, of course? Math, right, to actually do that. All right, so we've got physics. Now, so I'm a chemical engineer, right? The chemical engineer says, oh, sweet, I've got like a chemistry problem. If I burn, what did I say, 1 kilogram of what I call it, super awesome jet fuel, right? 1 kilogram of super awesome jet fuel, how much energy are we going to get out of it? I don't know, how much ever that is. We can measure it. We can just put one in there and see how high the rocket goes, whatever, right? Now we have another problem. Where are my aerospace guys? Carson, you're an aerospace guy, right? What's the problem with my engine?
You don't know like how much force it puts out.
Yes, and fundamentally, is my engine 100? If I put 100 joules into that engine, do I get 100 joules out of it? No, because there's some efficiency loss, right? So now we have, let's go over here, keep it separate. We have mass fuel equals, let's call it A, per weight. Or actually, we won't use weight because remember weight is what? Mass times gravity, right? Don't want to confuse anybody. So A per mass. Okay, so how do we calculate how much fuel we need now? Again, I don't need the exact formula. I'm just fundamentally, how do we calculate how much fuel we need? Okay, so we know how much work it's going to take to lift our rocket. How much fuel do I need to burn? Enough fuel to make that, right? So we need to burn enough fuel to get our rocket up. Easy enough, right? Just do the math. What's it take to lift say a 1,000-pound rocket? We just need to do the math. What's the problem we run into now? What's that? The weight of the fuel, my man. All right, so yeah, as we add fuel to the rocket, now we have to actually lift that fuel up. So then we add a little bit more fuel to the rocket to lift the fuel up. Now what do we have to do? Add a little bit more fuel to the rocket, and then we add more fuel, and then what happens? Right? So it's not infinite because it's little by little by little, right? But so we have to calculate not only, right, and this is the engineering part of this, right? It's not just your physics problem that you have in class, which is you need to lift a book from the, you see it all the time probably in physics class. If the book falls from the desk to the floor, how much, right? We have to continue to think about what we're going to do. Now, let me take it to so we have that here. So let me take it to the next step, which is how much fuel do we need? And that's a kind of a trick question. Why is that a trick question, Andrew? I see you smiling.
Well, I mean, it depends really on the efficiency you're going to get out of that. And you're going to need like caloric density of the fuel, or how much energy it's going to release when you burn 1 kilogram. And also, like if you're talking from like a cost standpoint, if you're going to use like less efficient fuel, you're going to need bigger fuel tanks, depending on the density of fuel. So I mean, you kind of have to optimize that as well.
Yes, and actually you bring up an interesting point because let's say your rocket only has so big of a fuel tank, that in of itself should limit how high your rocket's able to go, right? So now you actually have to go redesign your rocket. Your rocket just got bigger, and now we're all the way back to the drawing board. So you guys start to understand the problem that I'm having here is you can't just plug it into a formula. And that kind of sucks for those of us who are used to this kind of thinking in school where we have a problem, we're given the parameters, and we need to spit out the answer. So what we're going to do next week with our Units Conversions Lab, we're also going to take a look at Excel. Excel is a spreadsheet. I know most of you guys use Google Sheets, I think, just because it's free and accessible, right? We're going to be using Excel next week, so I need everyone to please bring their laptops if they have them. What we're going to be looking at is spreadsheets as a tool for solving this problem, because what you can do in a spreadsheet is you can actually remember how we said line 1, we need this much fuel, now we need more fuel. Imagine that in a spreadsheet where your spreadsheet's calculating it for you. It weighs this, how much fuel do I need? And then you take the cell from above, plug it into row 2, and row 2 says, now I need this, now I need this, now I need this, and you drag it down, and eventually you hit to the point where you're just putting a little teensy drop of fuel, and at that point it doesn't matter anymore because we're ignoring friction to begin with, right? So we're probably not going to make it as it is, but you guys see where I'm going with this, right? So that's what we're going to do next week. Now I have the next question to ask. So let's say we figure out exactly how much fuel we need. We have a 1,000-pound rocket, and I've been using pounds and metric, so just go with it, right? 1,000-kilogram rocket, and we've got 100 kilograms of fuel. What happens to our fuel as we go higher? What's that? There's less fuel, so it weighs less, right? So it's not just the amount of fuel that we need on the ground, is it? We actually, because then, going back to Andrew, if our rocket gets into space and it's got extra fuel left, what did we just do? Wasted a ton of money, right? Because we spent fuel lifting something that we didn't need to lift, right? So not only do we end up with fuel in space that we paid for that we didn't use, but we burned extra fuel getting that fuel up into space, right? So we as engineers need to go through this, and we need to calculate exactly how much we need, because it's not just because we want to know exactly how much we need, because it literally costs NASA or whoever's doing this, SpaceX, Blue Origin, whoever it is, right? It's costing these guys money to make this happen, right? So this is a pretty simple example, but it really starts to combine everything that we've been talking about into one simple problem, right? So this isn't the kind of problem that you're going to solve in physics class. You're going to solve one part of it. In chemistry class, we solved if I burn a peanut, right? Did you guys do that in calorimetry? You burn a peanut or a Frito chip or something like that and see how much it raised, right? Did your calorimetry lab, right? That's all it is, right? You're burning your fuel, you're seeing how much you're getting out of it, right? Now you hope that Mega Awesome Fuel Corp, super awesome jet fuel, you hope that they have a spec that they know how much you're getting out of it, right? And which makes your job easier. But if you have to, go back and do the calorimetry lab. Kate was nodding, she knows what she was doing. So you can have her do that part for you. Andrew can figure out how high the rocket needs to go. Vikram can figure out how efficient the engine is, and we can all get together and solve this problem, right? Now at a way, way, way bigger scale, that's what they're doing up at Boeing. But that's fundamentally what you do to get that rocket off the ground. Or again, Blue Origin or NASA, NASA's not designing anything, right? But fundamentally, I think you guys get what I'm picking up, right? All right, so this actually went way quicker than I thought. Does anybody have any questions? Because that is the end of class. Simple enough. We're all aerospace engineers now, right? You can launch a rocket. Okay, all right, but seriously, so next week, let's bring our spreadsheets, and we're actually going to do this problem. We're going to build the spreadsheet together, and we're going to have it spit out an answer for us. Okay, spreadsheets are an exceedingly valuable engineering tool. I use them quite literally every day, except sometimes on Saturdays. But all right, anything else? Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD. While the textbook is not essential to successfully follow all class videos, it is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.